Hello, and welcome to Cosmic Sleep Stories. Tonight, we'll drift into a tranquil journey through the cosmos and beyond, exploring 100 gentle, sleep-inducing facts that will carry you softly into the night. Greetings, dear traveler. How wonderful that you have found your way to this quiet corner of the universe. Tonight, we will wander together through some of the gentlest riddles that rest at the edges of human wonder. Silent questions that float like whispers across the fabric of everything we see and do not see. In this very instant, above and beyond, the heavens stretch endlessly, filled with radiant points of light. Each star, each swirling galaxy, has sent its luminous message across distances beyond measure, traveling through the void for eons untold, just to reach your eyes in this peaceful moment. It is a humbling thought, is it not? Despite our instruments, despite the elegance of our theories and the depth of our observations, we still cannot name what fills most of the cosmos. We have charted where the galaxies drift. We have listened to the ancient echoes of creation. We have measured the age of time itself. Yet beneath all this knowing, something else lingers, something vast and invisible, subtle and powerful, woven through the stars yet unseen by any eye. These hidden elements shape the universe on scales so grand they dwarf our imagining, guiding the graceful spin of galaxies, coaxing the expansion of space itself, and gently rewriting the very boundaries of what our science can describe. We can trace their influence like footprints in fresh snow. We know they are present, but their true nature remains veiled. And so our journey begins here, in the quiet mystery of the unseen. All throughout the cosmos, galaxies turn, immense spirals of starlight and nebulae gliding through the darkness. Yet when scientists first measured the pace of their rotation, something curious emerged. The stars far from the galactic heart were moving far more swiftly than expected. According to the gravity arising from all the visible matter, those distant stars should have drifted away into the endless night. Instead, they remained, held in their orbits as though cradled by some gentle, invisible embrace. This unseen presence has come to be called dark matter. The name does not suggest menace, but simply absence of light. It neither glows nor reflects, nor absorbs the spectrum we can perceive. It is invisible to every telescope, to every detector tuned to the electromagnetic chorus. And yet its presence is undeniable, revealed not by sight, but by the way it guides the motion of galaxies, bends the paths of light around massive clusters, and shapes the grand architecture of the universe itself. It quietly outweighs all the familiar matter we observe, the stars and planets and glowing gas, by a factor beyond imagining. In truth, dark matter is the dominant sculptor of cosmic structure. We simply do not yet know what it is made of. The story of this discovery begins many decades ago, in the early years of the last century, with a Swiss astronomer named Fritz Zwicky. While observing a collection of galaxies bound together in space, known as the Coma Cluster, he noticed something peculiar. The galaxies within this cluster were moving at such speeds that they ought to have drifted apart long ago, scattered like seeds on the wind. But they had not. They remained together, held by an unseen gravitational hand. Zwicky proposed that some hidden mass, a substance he termed dark matter, must be weaving the cluster into a coherent whole. His ideas were met with quiet skepticism and set aside for many years. Yet in the decades that followed, a pioneering astronomer named Vera Rubin, working alongside Kent Ford, turned her attention to individual galaxies and measured how stars move within them. What she observed confirmed the same gentle anomaly. Stars far from the galactic center were orbiting far more quickly than the visible matter could account for. The gravitational embrace of luminous stars and gas alone could not explain the motion. Since that time, galaxy after galaxy has revealed the same signature, the same flat rotation curve that refuses to decline with distance, as older theories had foretold. It is as though each galaxy rests within a vast invisible cocoon, a halo of unseen mass that pervades the space around and through the luminous spiral. Even when galaxies drift together and merge, the dark matter behaves differently from ordinary gas or stars. It glides through the collision like mist through a forest, undisturbed and unhindered. One of the most striking examples of this behavior can be found in a cosmic event known as the Bullet Cluster, where two great clusters of galaxies have gently passed through one another. By studying the way light bends around this system, a technique known as gravitational lensing, astronomers were able to map where the true mass resides. The map did not align with the glowing clouds of ordinary matter. Instead, it matched perfectly with the dark, the invisible. Gravitational lensing has become one of the most powerful methods for tracing dark matter indirectly. When light from a faraway galaxy travels toward us and passes near a massive cluster along the way, the cluster acts as a lens, bending and warping the image we receive. By carefully analyzing these distortions, scientists can create maps of mass distribution in the foreground, even when that mass cannot be seen directly. Time and again, these maps reveal far more mass than all the stars and gas combined can provide. And yet, despite this overwhelming circumstantial evidence, dark matter continues to elude direct observation. We can describe its effects with remarkable precision. We can calculate how much of it must exist, but the particles themselves, the fundamental substance of dark matter, remain beyond our grasp. They do not appear to interact with ordinary matter through electromagnetism or through the strong force that binds atomic nuclei. They respond, it seems, only to gravity, and even that interaction is extraordinarily gentle. So what could this mysterious substance be? Over many years, physicists have imagined a variety of possible particles that might account for dark matter. One early and thoroughly studied possibility is known as the WIMP, short for weakly interacting massive particle. These hypothetical entities would interact with ordinary matter through the weak nuclear force, but not through electromagnetism, which would explain their invisibility. Their expected mass and behavior arise naturally in several extensions of our current understanding of particles, including a framework known as supersymmetry. For a long time, WIMPs were considered the leading candidates. Entire underground laboratories were constructed deep beneath mountains and old mines, shielded from background noise, waiting patiently for the rare moment when a WIMP might collide with an atomic nucleus and reveal itself. But those moments have not yet come. As experiment after experiment returned empty results, attention has gradually turned toward other possibilities. One such candidate is the axion, a delicate, nearly weightless particle originally proposed to resolve a subtle puzzle in the theory of the strong nuclear force. Axions are extraordinarily light, yet they could exist in such staggering abundance throughout the cosmos that together they form a significant reservoir of mass. Specialized detectors are now listening for the faint signals axions might produce as they transform into photons within strong magnetic fields. Other ideas venture further still. Some researchers explore sterile neutrinos, particles that barely interact with anything at all. Others consider hidden sector particles, entire families of matter that exist parallel to our own, but remain invisible. There are even proposals that dark matter might take the form of ancient black holes, born in the first moments after the universe began. Still, other scientists suggest that dark matter may not be a particle at all, but rather a sign that our understanding of gravity itself needs to be gently revised, an approach sometimes called modified Newtonian dynamics. Yet none of these possibilities have fully answered the riddle. What dark matter is made of remains uncertain, but what it does, the way it shapes the cosmos, is becoming ever clearer. In fact, without dark matter, the universe as we know it simply could not have come to be. In the earliest epochs, shortly after the birth of space and time, ordinary matter was far too hot and energetic to settle into structures. It interacted intensely with light, which prevented it from clustering together. But dark matter, unaffected by radiation, was free to begin forming regions of greater density even in those primordial moments. These became the gravitational seeds into which ordinary matter would eventually drift and gather. In this way, dark matter acted as a framework, a scaffold upon which the visible universe could be built. Tiny ripples in the density of dark matter provided the foundations around which galaxies, clusters, and superclusters could slowly grow. Simulations of cosmic evolution illustrate this beautifully. When dark matter is included in the models, the resulting structure, a web of filaments and voids stretching across the universe, mirrors precisely what we observe in the night sky. Without dark matter, the cosmos would look nothing like it does. There would be no galaxies, no star clusters, no suns, and very likely no life. But dark matter's role is not confined to the distant past. It continues to play an active part in holding galaxies together even now. Its presence explains the stability of spiral galaxies, like our own Milky Way, the graceful shapes of galaxy clusters, and the delicate patterns imprinted in the cosmic microwave background, the faint afterglow of the universe's fiery beginning. These subtle ripples in ancient light align perfectly with predictions of a cosmos where dark matter outnumbers ordinary matter by a factor beyond simple counting. This is not merely a mathematical adjustment to account for missing mass. Dark matter is interwoven into the very blueprint of cosmic creation, and yet we still have not captured it directly, not with certainty, not without doubt. The scaffolding holds the universe together, but the beams themselves remain invisible to our eyes and instruments alike. Why then has it proven so elusive? Despite many decades of effort, not a single confirmed dark matter particle has been observed in a laboratory setting. The difficulty lies in the nature of interaction, or rather, the profound lack of it. Ordinary matter reveals itself in countless ways. It carries charge, it emits light, it radiates heat, it resists motion through friction. Dark matter, by contrast, appears to interact only through gravity and perhaps the weak nuclear force. This makes it astonishingly difficult to detect. Billions upon billions of dark matter particles may be passing through your body every second, drifting silently through the atoms and molecules that compose you, leaving no trace whatsoever. Experiments designed to catch these particles, such as those hunting for WIMPs, depend on the exceedingly rare event of a dark matter particle striking an atomic nucleus and transferring a tiny whisper of energy. These detectors are buried deep underground, far from the surface, shielded by layers of rock that block cosmic rays and other sources of interference. Yet even with extreme sensitivity and years of patient observation, the results have remained frustratingly silent. Other methods have also been tried. Some researchers search for the faint glow that might result if dark matter particles collide and annihilate one another in the dense cores of galaxies. Others look for signs of dark matter being produced in particle accelerators, such as the Large Hadron Collider, where protons smash together at energies approaching those of the early universe. Yet no clear signal has emerged. It is possible we have been looking in the wrong places or for the wrong things. Part of the challenge may lie in the assumptions that guided early searches. Many experiments were tuned to detect particles within a specific range of masses, inspired by elegant theories such as supersymmetry. As those ranges are progressively ruled out, the field of possibilities grows wider and more uncertain. Dark matter could be lighter than expected, or heavier, or more diffuse, or something altogether stranger. It may not take the form of particles as we currently understand them. It could behave like a field, spread smoothly across space. It might interact with itself in subtle ways we have not yet imagined. Or, in a more radical turn, it could be a hint that our understanding of gravity itself, the way mass and space-time relate, requires a deeper transformation. Each path leads into uncharted realms of physics, where the familiar landmarks fade and new principles await discovery. And that is what makes dark matter so deeply meaningful. This is not merely a matter of a missing ingredient in a cosmic recipe. It is a sign that our entire conception of matter, of what the universe fundamentally consists of, may be incomplete. The standard model of particle physics, which describes the behavior of all known particles and forces, is one of the most thoroughly tested and successful theories in the history of science. Yet it does not include dark matter. Whatever dark matter turns out to be, it lies beyond the boundaries of our current framework. This means the mystery is not only a problem for cosmology, the study of the universe as a whole. It is also a doorway into new physics. If we can come to understand dark matter, we may discover entire realms of particles, fields, and forces that have existed all along, invisible and unnoticed. Our present view of matter rests on a small collection of familiar building blocks: protons, neutrons, electrons, quarks, and the forces that bind them together. But nature may be far richer and more varied than we have dared to imagine. Dark matter could be the first glimpse of a shadow sector of physics, a hidden world with its own symmetries, its own particles, its own dynamics running parallel to the luminous world we inhabit. This possibility reshapes how we think about the cosmos in the most profound way. The matter we can see, all the stars that glitter in the night, all the glowing gas and dust, even the planets and moons and every living being, might be nothing more than a thin, luminous layer floating atop a far deeper and darker ocean. We have spent centuries studying the visible universe, mapping its structures, tracing its history, uncovering its laws. But if dark matter truly dominates the cosmos, then most of the universe remains invisible to us, not just in appearance, but in essence. This is a humbling realization. It suggests that what we have long called normal matter may not be normal at all, merely familiar. The universe we know may be only a small radiant island in a vast dark sea. In recent years, the search for dark matter has grown more inventive and more determined. New generations of detectors are pushing the limits of sensitivity to levels once thought impossible. These experiments are exploring weaker interactions, lighter masses, and subtler signals than ever before. Some now target ultralight candidates using resonant cavities, delicate superconducting circuits, or even vibrating crystals that might register the faintest whisper of dark matter passing through. Others turn their gaze skyward. Space-based observatories scan the heart of our galaxy, searching for faint glimmers that might arise if dark matter particles collide and annihilate. Gravitational wave detectors, originally built to listen for ripples in space-time from merging black holes, are now exploring whether dark matter could consist of tiny primordial black holes born in the earliest moments of creation. Still others employ quantum technologies using clouds of cold atoms, interferometers, or nanoscale sensors capable of detecting gravitational tugs too gentle for earlier instruments to notice. But with each new approach comes greater complexity and deeper questions. What if dark matter is not a single substance, but a mixture of several? Could it be composed of multiple components, just as ordinary matter includes many different kinds of particles? Might dark matter interact with itself in subtle ways, forming invisible structures or dissipating energy through processes we have not yet imagined? And perhaps most unsettling of all, what if dark matter does not exist? What if the evidence we observe points not to missing mass, but to a fundamental misunderstanding of gravity itself? Theories of modified gravity, which propose that the force of gravity behaves differently on very large scales than we expect, offer alternative explanations for the motions of galaxies and the bending of light. These ideas remain controversial and incomplete, unable to account for all the observations as successfully as dark matter does. Yet they remind us that certainty is elusive and that nature may surprise us in ways we cannot yet foresee. The truth is, we do not yet know the answer, and that uncertainty, while at times frustrating, is also what makes this search so deeply meaningful. Because to solve the riddle of dark matter is to come face to face with the boundaries of knowledge itself. We are no longer simply measuring the masses of galaxies or mapping invisible halos. We are testing the very limits of our theories, our instruments, and our understanding of what the universe is made of. And in doing so, we are reminded that the cosmos still holds secrets, vast, invisible, and waiting patiently to be uncovered. It may seem difficult to believe, but the story grows even stranger and more wondrous. In the closing years of the last century, two independent teams of astronomers turned their attention to distant supernovae, brilliant stellar transformations that serve as cosmic signposts. They hoped to measure how quickly the universe's expansion was gradually slowing, drawn back by the mutual gravitational embrace of all the matter it contains. Gravity, after all, draws things together. So the expectation was that over time, the expansion born in the fiery beginning would be gently decelerating. But when the observations were analyzed, the astronomers were astonished. The supernovae appeared dimmer than anticipated, farther away than they should have been. The universe was not slowing down at all, it was speeding up. This revelation that cosmic expansion is accelerating rather than slowing shook the very foundations of cosmology. Something was coaxing space itself to stretch faster and faster, acting in opposition to gravity's inward pull. But what could it be? The simplest explanation, first imagined by Einstein many decades earlier and then quietly set aside, was a kind of intrinsic energy woven into the fabric of space itself, often called the cosmological constant. Yet even this idea raised thorny and delicate questions. If space contains energy, how much should it hold? Why does it possess precisely the amount we observe? And where does this energy come from? Unable to answer these riddles, physicists gave the phenomenon a new name: dark energy. But like dark matter, it remains unseen, known only by the effects it produces, the gentle acceleration of galaxies drifting ever farther apart. At first glance, dark energy and the cosmological constant might sound like two names for the same idea, but there is an important distinction worth noting. The cosmological constant, often represented by the Greek letter lambda, is a fixed quantity, a uniform energy density that fills space evenly and never changes with the passage of time. It was introduced by Einstein as an adjustment to his equations, a way to keep the universe static and unchanging. Later, when the expansion of the universe was discovered, the cosmological constant was discarded, thought to be unnecessary. But now, in light of the accelerating cosmos, it has returned, not as an error, but as a serious possibility. Dark energy, by contrast, is a broader term. It includes the cosmological constant, but also allows for more exotic possibilities. What if this energy is not constant at all? What if it evolves and changes over time? These alternatives are sometimes grouped under the name quintessence, and they describe dark energy as a field that varies across space and time, much like other fields in physics. Depending on its behavior, it could lead the universe to expand forever, growing colder and emptier, or it could slow down again in some distant future epoch, or even reverse direction. But no matter which model one considers, the effect is the same. Dark energy dominates the large-scale behavior of the universe. Roughly 2/3 of the universe's total energy content appears to be in the form of dark energy. It does not clump together like matter does, and it does not thin out as space expands. Instead, it exerts a kind of gentle outward pressure, a repulsive influence woven into the very fabric of space-time itself. This subtle yet persistent coaxing affects how quickly the universe expands, how cosmic structures grow and evolve, and even the ultimate destiny of everything we know. Over the span of billions upon billions of years, dark energy has quietly reshaped the cosmos. In the early universe, matter, both ordinary and dark, was the dominant force. It gathered clouds of gas together, kindled the first stars, forged galaxies, and carved the grand cosmic web that stretches across the heavens. But as the universe continued to expand, the density of matter gradually decreased, while the influence of dark energy remained steady, or perhaps even grew. At a certain moment, many billions of years ago, dark energy overtook matter as the guiding force of cosmic evolution. Since that turning point, galaxies have drifted farther and farther apart. The expansion has accelerated, and the structures of the universe have begun to settle into a kind of frozen stillness. This acceleration means that distant galaxies are now receding from us at ever-increasing speeds. Eventually, regions of space beyond a certain threshold will move away faster than light itself can bridge the distance. Those galaxies will gradually fade from view, becoming forever unreachable. Cosmic isolation will deepen. In unimaginably distant times, the night sky could grow dark once more, not because the stars have faded, but because the universe has expanded so much that their light can no longer cross the void. The future may hold not only silence, but solitude on a cosmic scale. And yet this is only one possible fate, based on what we currently think dark energy might be. The truth is, we do not yet know. Is it truly constant and unchanging? Is it evolving? Is it even real? Or is it a sign that our understanding of gravity itself requires a deeper revision? Just as with dark matter, these are not questions of idle curiosity. They cut to the very heart of physics, to the nature of space and time themselves. To study something as elusive as dark energy, astronomers rely on the universe itself as their laboratory. Supernovae, the brilliant transformations of dying stars, are one of the most powerful tools. These stellar events occur in binary systems, where a white dwarf gradually accretes matter from a companion star until it reaches a critical threshold and undergoes a luminous transformation. Because they occur under similar conditions, they have nearly uniform intrinsic brightness. This makes them what astronomers call standard candles, objects whose distances can be estimated by comparing their known luminosity with how bright they appear in our telescopes. By measuring the redshift of these supernovae, the degree to which their light has been stretched by the expansion of space, astronomers can reconstruct how the universe has expanded over the course of cosmic history. That is how the acceleration was first discovered, and ever since, these stellar beacons have continued to trace the cosmic expansion, providing essential evidence for dark energy's influence. But supernovae are not the only line of evidence. The cosmic microwave background, the faint afterglow of the universe's fiery beginning, provides a snapshot of the cosmos as it was in its infancy, when it was only a small fraction of its current age. Embedded in this ancient light are tiny fluctuations in temperature, delicate ripples that encode information about the geometry, contents, and history of the universe. When dark energy is included in the models scientists construct, the positions and strengths of these fluctuations align beautifully with what is observed. Without it, the picture does not fit. Other methods include studying baryon acoustic oscillations, which are subtle patterns in the distribution of galaxies, and weak gravitational lensing, where the shapes of distant galaxies are gently distorted by the presence of intervening mass. Together, these various approaches converge on the same conclusion. The expansion of the universe is accelerating, and dark energy, or something that mimics it, is real. But the what and the why remain unresolved. The leading theoretical explanation that dark energy arises from the vacuum energy of empty space turns out to be deeply puzzling. Quantum field theory tells us that even a perfect vacuum is not truly empty. Instead, it gently fluctuates with temporary particle-antiparticle pairs that appear and vanish in the briefest of instants. These quantum fluctuations should give rise to a non-zero energy density throughout space, and in theory, this vacuum energy should behave exactly like the cosmological constant. But when physicists attempt to calculate how much energy this vacuum should contain, the numbers become wildly inconsistent. The theoretical result is larger than what we observe by a factor so enormous it defies comprehension. a discrepancy spanning many orders of magnitude. This mismatch is often described as one of the worst theoretical predictions in the history of physics. Why is the vacuum energy so extraordinarily small? Why is it not zero? And why does it happen to be roughly similar in magnitude to the matter density of the universe right now, at this particular moment in cosmic time? These questions have no satisfying answers. Some physicists suspect an unknown symmetry cancels most of the vacuum energy, leaving only the tiny remainder we observe. Others invoke the anthropic principle, the idea that we find ourselves in a universe with this particular value because only such universes can support the emergence of complexity and life. But these are not fully predictive explanations. They are placeholders, gentle markers on the path toward a deeper understanding still to come. In response to this puzzle, other theories have emerged. Quintessence models propose a dynamic field, similar in spirit to fields found elsewhere in physics, that slowly evolves over time. Unlike a constant, its influence can grow or diminish depending on the properties and behavior of the field. This opens the door to a wider range of possible cosmic futures, but it also makes the physics harder to pin down. The space of possibilities becomes vast, and without firm observational constraints, many models remain speculative. Still, some leave subtle signatures, gentle changes in the equation of state of dark energy, or variations in its density with distance and time. Future surveys and observations hope to test these possibilities. One of the most striking consequences of dark energy is its effect on the geometry of space-time itself. In general relativity, the distribution of energy and matter determines the curvature of space. In a universe dominated by matter, the curvature depends on the total density. If it is high, space curves gently inward, creating what is called a closed universe. If it is low, it curves outward, forming an open universe. But dark energy, particularly when it behaves like a cosmological constant, alters that relationship in subtle and profound ways. It does not gather into clumps like matter does, nor does it thin out as the universe expands. Instead, it acts as a constant gentle pressure, stretching space and coaxing the passage of time from one cosmic epoch to the next. Observations of the cosmic microwave background, studies of large-scale galaxy clustering, and measurements of gravitational lensing patterns all suggest that the universe is remarkably flat on the larger scales, precisely what one would expect in a cosmos delicately balanced between matter and dark energy. But it is a fragile balance. Even slight changes in the amount or behavior of dark energy would shift the geometry, altering how light travels, how structures grow, and how the universe unfolds over time. This expansion is not merely a gentle swelling. It quietly rewrites the ultimate destiny of the cosmos. If dark energy is truly constant, unchanging throughout all of time, then galaxies will drift ever farther apart. Stars will eventually exhaust their fuel and fade, and the universe will grow colder and emptier with each passing eon, a future sometimes called the Big Freeze. But if dark energy strengthens over time, as in certain exotic models known as phantom energy, it could lead to an even more dramatic fate where the expansion becomes so extreme that eventually even the bonds holding atoms together are gently pulled apart, an ending sometimes called the Big Rip. Alternatively, if dark energy somehow decays or reverses its influence, the cosmos could one day collapse back upon itself in what is known as the Big Crunch. The shape of tomorrow hinges entirely on the nature of dark energy, and right now, we are still only beginning to understand. To close the gap between theory and observation, physicists and astronomers have turned to a new generation of instruments and surveys. The Euclid Space Telescope, launched by the European Space Agency, is mapping countless galaxies to chart the expansion history of the universe and trace the influence of dark energy over vast stretches of cosmic time. The Vera C. Rubin Observatory in Chile, with its ambitious survey known as the Legacy Survey of Space and Time, will observe the entire visible sky repeatedly, building an unprecedented catalogue of transient events and gravitational lensing effects. NASA's Nancy Grace Roman Space Telescope will complement these efforts using wide-field infrared imaging to detect subtle signatures of cosmic acceleration. Each of these missions is designed not just to confirm the presence of dark energy, but to constrain its properties, to test whether it behaves like a cosmological constant or something more intricate and dynamic. These experiments may help determine whether dark energy evolves over time, whether it gathers in unexpected ways, or whether it connects with deeper layers of particle physics and field theory still waiting to be uncovered. But for now, many questions remain wide open. What is the true nature of dark energy? Why did it begin to dominate the universe's expansion only relatively recently in cosmic history? Is it related to quantum fields, to vacuum energy, or to something stranger still? Does it point toward extra dimensions, multiverse frameworks, or undiscovered symmetries in the laws of nature? Or is it a hint that general relativity itself, the very fabric of space-time, requires a deeper revision? In many ways, dark energy is not just a phenomenon. It is a boundary, a vast expanding edge to our understanding. We know it is present. We feel its influence in the motion of galaxies and the dimming of distant stars. But its cause, its meaning, its place in the puzzle of the cosmos, those remain gently veiled. Black holes are among the most mysterious and profound objects in the universe. They begin as a consequence of gravity taken to its absolute limit. When a massive star exhausts its nuclear fuel, nothing remains to resist the inward pull of its own immense weight. If the collapse is complete, the core compresses beyond all known states of matter, forming what is called a singularity, a point where density becomes unimaginable and space-time itself seems to break down. Around this singularity forms the event horizon, a boundary beyond which nothing, not even light, can return. It is not a physical surface, but rather a threshold, a point of no return. Cross it, and the journey back becomes impossible. At the heart of a black hole, our familiar laws of physics begin to falter. General relativity, which describes gravity and the curvature of space-time, predicts the formation of the singularity, but it also signals its own incompleteness there. Unimaginable density, infinite curvature. These are signs that a more fundamental theory is needed. Quantum mechanics, which governs the behavior of particles on the smallest scales, has no answer for what happens at the center of a black hole. The event horizon shields that mystery from view, locking it behind a veil that no signal can pierce. We know the black hole exists, but not what truly lies within. For many decades, it was thought that black holes were simple, defined entirely by their mass, charge, and spin. They could swallow stars, gas, even light itself, but they gave nothing back, just a dark gravitational presence. Then, in the early 70s, Stephen Hawking changed everything. Combining ideas from quantum field theory and general relativity, he showed that black holes are not completely black. Instead, they emit a faint glow of particles, now known as Hawking radiation. This radiation arises from quantum fluctuations near the event horizon. In the quantum realm, even empty space gently fluctuates with temporary particle-antiparticle pairs that appear and disappear in the briefest instants. Near a black hole, the intense curvature of space-time affects these fluctuations in such a way that, to an observer far away, it appears as though the black hole is slowly radiating particles. From a distance, it looks as if the black hole is gradually evaporating. This was a revolutionary insight, but it led to a deep and troubling problem. As the black hole emits Hawking radiation, it loses mass. Over immense stretches of time, if no new matter falls in, it shrinks. Eventually, it may evaporate entirely, vanishing into a final whisper of radiation. But here is the paradox. What happens to the information about everything the black hole once consumed? In quantum mechanics, information is never truly lost. The evolution of a closed system is reversible. But in Hawking's picture, the radiation appears completely thermal, carrying no imprint of the black hole's internal contents. If the black hole disappears and the information is not encoded in the radiation, then it is lost forever. This violates one of the core principles of quantum theory. It sparked what has become one of the most profound puzzles in theoretical physics: the black hole information paradox. How can we reconcile Hawking radiation, which seems to destroy information, with a universe that at its most fundamental level should preserve it? The stakes are enormous. If information can be lost in black holes, then quantum mechanics itself may be incomplete. If it cannot, then something about our understanding of black holes or space-time must change. And the paradox only deepens the more closely we examine it. One of the most surprising developments in black hole physics was the realization that black holes possess entropy. In classical physics, entropy is a measure of disorder, or more precisely, of the number of microscopic configurations that correspond to a given macroscopic state. A glass of water has entropy. A star has entropy. But a black hole, it seemed too simple, defined only by mass, spin, and charge. It appeared to lack the internal degrees of freedom that give rise to entropy. And yet, Hawking's work, along with that of Jacob Bekenstein, revealed that black holes must have entropy proportional to the surface area of their event horizon, not their volume. This was a profound shift. It suggested that the information content in a black hole scales with its boundary, not what lies inside, but what rests on the edge. Bekenstein's formula, later refined by Hawking, shows that the entropy of a black hole is proportional to the area of the event horizon divided by the Planck length squared. That means the entropy of a black hole is immense, far greater than that of ordinary matter of the same mass. This connection between area and entropy led to the holographic principle, the idea that the fundamental description of a region of space may be encoded on its boundary, like a hologram. But understanding exactly what those microstates are and how they store information requires a theory of quantum gravity. General relativity describes black holes as smooth geometrical objects, while quantum mechanics demands a granular, probabilistic structure. Reconciling the two requires a deeper framework, one that can describe space, time, and information on the smallest possible scales. Several approaches have tried to bridge the gap. In string theory, black holes can be modeled using collections of strings and branes whose quantum configurations match the expected entropy. Loop quantum gravity, another candidate theory, describes spacetime as a network of discrete loops, which might account for black hole microstates in a different way. But no theory has yet emerged as definitive, and the paradox remains. One proposed resolution is that the information is somehow encoded in the Hawking radiation after all, that it is not truly thermal, but subtly entangled with the interior of the black hole. As the black hole evaporates, quantum correlations might allow the information to escape in a scrambled but recoverable form. This would preserve unitarity, the rule that quantum evolution is reversible, and save the foundations of quantum theory. But it raises new questions. How does the information get out? Through what mechanism? And if it escapes, does that challenge the idea that nothing can travel faster than light? To address this, some physicists proposed a dramatic possibility: the firewall hypothesis. According to this idea, the smooth horizon of a black hole is an illusion. Instead, an infalling observer would encounter a wall of high-energy radiation, a firewall at the horizon where quantum entanglement breaks down. This would allow information to escape, but at the cost of violating another cherished principle of physics, the equivalence principle, which says that free fall through empty space should feel smooth and uneventful. The firewall proposal preserves unitarity, but only by sacrificing general relativity's core symmetry. It is a bold move, and one that remains highly controversial. Some researchers view firewalls as a sign that we have reached the limits of our current framework. Others see them as an artifact of overly strict assumptions, but all agree the resolution to the black hole information paradox will likely involve new physics, perhaps even a new understanding of what space, time, and information really are. Despite their mystery, or perhaps because of it, black holes have become invaluable tools for physicists. They are not just astrophysical curiosities. They are crucibles where the known laws of nature are gently pushed to their breaking point. In the intense gravity near a black hole's event horizon, time slows, space stretches, and tidal forces grow strong enough to reshape matter in the most profound ways. These are the most extreme conditions the universe naturally provides, conditions that cannot be replicated in any laboratory on Earth. Studying black holes allows us to test general relativity in its most extreme regime and probe the edge of quantum physics, where our current understanding begins to gently crack. In that way, every black hole is a natural experiment, a cosmic laboratory in which space and time are distorted beyond ordinary recognition. We cannot peer into the singularity itself, but we can observe the behavior of matter and light near the event horizon. We can measure the orbits of stars around black holes, as has been done at the center of the Milky Way, where a supermassive black hole named Sagittarius AA anchors our galaxy. We can study the accretion disks of hot gas swirling around black holes, emitting X-rays and high-energy radiation. And now, with the advent of gravitational wave astronomy, we can detect the ripples in space-time caused by the graceful mergers of black holes, signals that carry information directly from the most dramatic events in the universe. These observations provide essential data points, but the deeper tension remains. Black holes sit at the intersection of two great but incompatible theories. Quantum mechanics describes the probabilistic behavior of particles and fields on the smallest scales. It has been tested with exquisite precision. General relativity describes gravity as the curvature of space-time, and it has passed every observational test in the macroscopic world. But when we try to combine the two, especially in extreme environments like black holes, contradictions arise. The information paradox is one example. Singularities are another. And the failure to describe what happens inside a black hole shows that neither theory on its own is complete. This incompatibility has driven the search for a theory of quantum gravity, a unified framework that can describe all forces, all particles, and all scales. String theory and loop quantum gravity are leading candidates, but they remain mathematically intricate and difficult to test. Holography, inspired by black hole entropy, offers another promising path. According to a duality proposed in string theory, a gravitational theory in a higher dimensional space can be equivalent to a quantum field theory without gravity on its boundary. In this picture, a black hole in one universe corresponds to a quantum system in another, where information is preserved. This holographic principle has become a powerful tool for studying quantum gravity in highly symmetric spacetimes. Even if this specific duality does not apply to our universe directly, it suggests that space and time may be emergent, not fundamental ingredients of reality, but macroscopic effects that arise from deeper quantum structures. In such a view, black holes might not be puzzles within spacetime, but clues to how spacetime itself comes into being. And so, black holes continue to illuminate the deepest fault lines in physics. They demand that we confront the paradoxes we would prefer to ignore. They blur the lines between known and unknown, between the classical and the quantum, and they hint, perhaps more clearly than any other object, that the universe is governed by principles we have not yet fully grasped. At the forefront of black hole research, new ideas continue to challenge our assumptions and sometimes our imaginations. One avenue explores quantum entanglement as a possible bridge between the interior and exterior of a black hole. The so-called ER equals EPR conjecture, proposed by Juan Maldacena and Leonard Susskind, suggests that Einstein-Rosen bridges, or wormholes, and quantum entanglement may be two sides of the same coin. In this picture, particles that are entangled may be connected by tiny wormholes, and a black hole's interior could be related to the entangled structure of the Hawking radiation it emits. It is an elegant idea, though still speculative, and it hints that space-time geometry and quantum information may be more deeply intertwined than we have realized. Elsewhere, physicists are revisiting the notion of complementarity, the idea that different observers may have different but equally valid descriptions of the same physical system. From outside, a black hole looks like a hot radiating object with no visible interior. From the perspective of someone falling in, the event horizon is smooth, and nothing unusual happens upon crossing it. These views seem contradictory, but some theories suggest they can coexist, not through illusion, but through a deeper, unified description. What unites all these efforts is a shared recognition. Black holes are more than endpoints of gravitational collapse. They are crucibles of fundamental truth, places where the known laws of physics bend and where new ones are quietly forged, whether through string theory, holography, quantum information, or yet undiscovered principles. The study of black holes is guiding us toward a more complete picture of the universe, one that will not only resolve paradoxes, but perhaps explain what space, time, and reality themselves are truly made of. At the heart of modern physics lies a deep and unresolved tension. Quantum mechanics and general relativity are two pillars of scientific understanding. Each has been tested again and again, and each has proven remarkably successful in its own domain. Quantum theory governs the tiny world of particles and fields where uncertainty and probability reign. General relativity describes the vast architecture of space, time, and gravity, where matter tells space-time how to curve, and curvature tells matter how to move. But when the two theories meet in extreme conditions like black holes or the earliest moments of the universe, they clash. The rules of one break the framework of the other. They cannot both be entirely correct. This is the problem of quantum gravity. To find a theory that unites these two descriptions into a coherent whole, not a patchwork, not a truce, but a single self-consistent framework that reveals how space-time behaves at the smallest possible scales. It is not just a mathematical exercise. Without quantum gravity, we cannot fully understand the origin of the cosmos, the fate of black holes, or the true nature of space and time. It is one of the deepest unsolved problems in all of physics, and perhaps the most fundamental. One of the most ambitious and mathematically rich approaches to quantum gravity is string theory. In this framework, the fundamental building blocks of reality are not point-like particles, but tiny vibrating strings. Different vibrational modes of the string correspond to different particles: an electron, a photon, a graviton. One of the great strengths of string theory is that it naturally includes gravity. The graviton, a hypothetical quantum of the gravitational field, emerges from the theory without being inserted by hand. String theory also unifies the other fundamental forces, suggesting that all interactions may arise from a single underlying principle. But there is a catch. For the equations to work, string theory requires extra dimensions, not just the familiar 3 of space and 1 of time, but 10 or even 11 dimensions in total. These extra dimensions must be curled up or compactified at scales far smaller than atoms, hidden from view. There are also many possible ways to shape and fold these dimensions, each giving rise to different low-energy physics. This leads to the so-called string landscape, a vast range of possible universes, each consistent in its own right. Some physicists see this flexibility as a strength. Others see it as a lack of predictive power. An alternative to string theory is loop quantum gravity, a non-string-based attempt to quantize space-time itself. In this approach, space is not continuous, but composed of tiny discrete units, loops of quantum geometry. These loops form a network, or spin foam, which evolves over time according to specific quantum rules. In this view, space and time are not smooth backdrops, but emergent properties arising from the underlying quantum structure. Loop quantum gravity avoids the need for extra dimensions and is formulated entirely within the framework of general relativity and quantum mechanics. But it faces its own challenges. Recovering the smooth space-time of general relativity on large scales remains difficult, and connecting the theory to observable predictions has proven elusive. Both approaches, string theory and loop quantum gravity, represent serious attempts to bridge the gap between the quantum and the cosmic. Yet neither has achieved full success. The search for quantum gravity continues, guided by paradoxes, guided by black holes, guided by the hope that somewhere in the mathematics, the universe is whispering its deepest secrets. One of the most tantalizing aspects of quantum gravity is the possibility that space-time itself is not fundamental but emergent. In everyday experience, we think of space and time as the stage upon which events unfold. But in some approaches to quantum gravity, space and time arise from something deeper, from quantum information, from entanglement, from relationships between abstract mathematical structures. If this is true, then asking what existed before the Big Bang or what lies at the center of a black hole may be asking the wrong questions. Space and time may not extend indefinitely into the past or persist at the smallest scales. They may be macroscopic approximations, useful descriptions that break down when probed too closely. This is a radical idea, but it is one that has gained traction in recent years, particularly through the study of holography and quantum entanglement. It suggests that the universe may be far stranger than we have imagined, built not from particles moving through space, but from information woven into the fabric of reality itself. Another profound mystery lies in the very nature of the cosmos. Why does the universe contain matter at all? According to our best understanding, when the universe was born, matter and antimatter should have been created in equal amounts. For every particle of matter, an antiparticle of antimatter should have appeared. And when matter and antimatter meet, they annihilate one another, releasing pure energy. If this symmetry had held perfectly, the universe should have been left with nothing but radiation, a sea of light with no stars, no planets, no life. Yet here we are, made of matter, surrounded by matter, in a cosmos that is overwhelmingly composed of matter, with antimatter exceedingly rare. This profound imbalance is known as the baryon asymmetry, and it is one of the deepest unsolved puzzles in cosmology and particle physics. The riddle is not that matter exists, but that it exists in such overwhelming abundance compared to antimatter. Measurements of the cosmic microwave background and other observations suggest that for every several billion photons in the universe, there is roughly one baryon, one particle of ordinary matter. This tiny excess, this slight asymmetry in favor of matter over antimatter, is what allowed galaxies, stars, and eventually life to form. But where did this asymmetry come from? What process in the early universe tipped the balance, even by the smallest amount, in favor of matter? One of the most widely studied explanations is a process known as baryogenesis, the theoretical mechanism by which an excess of baryons, particles like protons and neutrons, was generated over their antimatter counterparts. For baryogenesis to occur, certain conditions must be satisfied. These are known as the Sakharov conditions, named after the physicist Andrei Sakharov, who first articulated them. The first condition is that baryon number, a quantity that counts the number of baryons, must be violated. In other words, there must be processes that can create or destroy baryons without creating an equal number of antibaryons. The second condition is that there must be a violation of charge parity symmetry, or CP symmetry. This symmetry states that the laws of physics should remain unchanged if particles are replaced with their antiparticles and their spatial coordinates are inverted. If CP symmetry were exact, matter and antimatter would behave identically, and no asymmetry could arise. The third condition is that these processes must occur out of thermal equilibrium, in a state where the universe is not perfectly balanced and reactions proceed at different rates. CP violation, the breaking of this symmetry between matter and antimatter, has been observed experimentally. It was first discovered in the gentle decay of particles called K-mesons, and more recently has been observed in other systems as well. The LHCb collaboration at CERN has even observed CP violation in the decay of baryons, the very particles that make up most of the matter in the observable universe. These observations confirm that the laws of physics do indeed distinguish between matter and antimatter in subtle but measurable ways. Yet the amount of CP violation observed in the standard model of particle physics, our current best theory of particles and forces, is not nearly enough to account for the enormous matter-antimatter asymmetry we see in the universe. Something more is needed, some additional source of CP violation, some new physics beyond the standard model that can generate the required excess of matter. One promising candidate is leptogenesis, a mechanism in which an initial asymmetry in the number of leptons, a class of particles that includes electrons and neutrinos, is later converted into a baryon asymmetry through complex interactions. In many models of leptogenesis, heavy neutrinos, particles that exist beyond the standard model, decay in ways that violate CP symmetry and produce more leptons than antileptons. Through subsequent interactions involving the weak force, this lepton asymmetry can be transformed into the baryon asymmetry we observe today. Leptogenesis is particularly appealing because it connects the matter-antimatter asymmetry to the properties of neutrinos, which are among the most mysterious and least understood particles in nature. If leptogenesis is correct, it would suggest that the reason we exist, the reason the universe is filled with matter, is intimately tied to the behavior of these elusive particles. Other theories propose different mechanisms. Some suggest that the asymmetry was generated during a phase transition in the very early universe, when the cosmos underwent a sudden change in its properties, much like water freezing into ice. Others invoke exotic processes involving grand unified theories, frameworks that attempt to unify all the fundamental forces at extremely high energies. Still others look to physics beyond the standard model, such as supersymmetry or extra dimensions, for new sources of CP violation. But despite decades of theoretical work and experimental searches, the origin of the matter-antimatter asymmetry remains unresolved. We know that something must have tipped the balance in the first moments after the universe was born, but we do not yet know what. It is a humbling reminder that even the most basic question, why does matter exist, still has no definitive answer. The asymmetry between matter and antimatter is not just a cosmological curiosity. It has profound implications for our understanding of the universe's history and its ultimate fate. If the asymmetry had been even slightly different, if the balance had tipped just a bit more or less, the universe might have been filled with nothing but radiation, or it might have collapsed back on itself before stars could form. The fact that we exist at all is a testament to the delicate tuning of physical processes in the early universe. It suggests that the laws of physics, as we currently understand them, are incomplete, and that somewhere in the equations, hidden in the mathematics, lies a deeper principle that governs the emergence of matter from the primordial fire. Beyond the mystery of matter and antimatter lies an even more speculative idea, the possibility that our universe is not alone. This is the concept of the multiverse, the notion that the cosmos we observe may be just one of countless others, each with its own properties, its own laws, its own history. The idea of a multiverse arises naturally in several areas of modern physics, particularly in the theory of cosmic inflation. Inflation is a theory that proposes the universe underwent a brief but extraordinarily rapid expansion in the first moments after its birth, smoothing out irregularities and setting the stage for the large-scale structure we see today. But in some versions of inflation, known as eternal inflation, the inflationary expansion never truly ends. According to eternal inflation, the universe is always inflating somewhere. Quantum fluctuations in the field driving inflation cause some regions to stop inflating and form pocket universes, like bubbles forming in boiling water. But other regions continue to inflate, producing more and more bubbles, each of which becomes a separate universe with its own distinct properties. This process goes on forever, creating an infinite multiverse in which our observable universe is just one tiny bubble among an endless sea of others. Each universe in this multiverse may have different physical constants, different particles, different forces. In some, the laws of physics might be wildly different from our own. In others, they might be nearly identical. Some universes might be lifeless and barren, while others might teem with complexity and life. The multiverse is a deeply controversial idea. On one hand, it arises naturally from well-motivated physical theories like inflation and string theory, which predict a vast landscape of possible vacuum states, each corresponding to a different universe with different properties. On the other hand, the multiverse is notoriously difficult to test. If other universes are forever beyond our reach, separated from us by vast distances or by the boundaries of space-time itself, then how can we ever hope to observe them or confirm their existence? Some physicists argue that the multiverse is not science, but philosophy, a collection of possibilities without empirical grounding. Others contend that the multiverse makes testable predictions, such as patterns in the cosmic microwave background or anomalies in the distribution of galaxies that could provide indirect evidence for its reality. One of the most intriguing aspects of the multiverse is its potential to explain why our universe appears so finely tuned for life. Many of the fundamental constants of nature, such as the strength of gravity, the mass of the electron, or the energy of the vacuum, seem to be delicately balanced in just the right way to allow stars, planets, and living beings to exist. If any of these constants were even slightly different, the universe might have been inhospitable to life. In a single universe, this fine-tuning seems puzzling, almost miraculous. But in a multiverse containing countless universes with different properties, it becomes a matter of probability. We find ourselves in a universe that is suitable for life simply because only such universes can produce observers like us. This is the essence of the anthropic principle, the idea that the properties of the universe we observe are constrained by the requirement that it must be capable of supporting life. While the anthropic principle offers a kind of explanation, it is not a satisfying one for many physicists. It does not tell us why the laws of nature take the form they do, only that we happen to live in a place where they do. The multiverse also raises profound philosophical questions. If there are infinitely many universes, then anything that can happen will happen somewhere. Every possible history Every conceivable outcome, every variation on the laws of physics, all exist in some corner of the multiverse. In such a framework, our universe loses its uniqueness. It becomes just one point in an infinite sea of possibilities. Some find this idea liberating, a reminder of the vastness and richness of reality. Others find it unsettling, a dissolution of meaning in an endless expanse of alternatives. Regardless of one's philosophical stance, the multiverse challenges us to think deeply about the nature of existence, the limits of scientific inquiry, and the relationship between observation and reality. String theory, as mentioned earlier, provides one of the strongest theoretical motivations for the multiverse. The theory's landscape, the vast collection of possible ways to compactify extra dimensions and configure vacuum states, suggests that there may be an enormous, perhaps infinite, number of possible universes, each corresponding to a different point in this landscape. Some string theorists embrace this diversity, viewing it as a feature rather than a flaw. Others seek ways to narrow down the possibilities, to identify principles that select a unique or preferred vacuum. But so far, no such principle has been found, and the landscape remains vast and largely unexplored. Loop quantum gravity, while less directly connected to the multiverse, also raises intriguing possibilities. If space-time is fundamentally discrete and quantum in nature, then the structure of the cosmos may be more varied and intricate than we can currently imagine. Some models in loop quantum gravity suggest that the Big Bang was not the beginning of time, but rather a bounce, a transition from a previous contracting phase to the current expanding one. If this is true, then the universe may be cyclic, undergoing endless cycles of expansion and contraction, with each cycle potentially giving rise to different properties and structures. In such a scenario, the multiverse becomes not a collection of separate bubbles, but a sequence of epochs, each one a new chapter in an eternal cosmic story. Another source of multiverse ideas comes from quantum mechanics itself. In the many worlds interpretation, every quantum measurement causes the universe to split into multiple branches, each corresponding to a different possible outcome. In this view, all possible histories are realized, not in separate universes scattered across space, but in parallel branches of a vast quantum wave function. While this interpretation is mathematically elegant and avoids some of the conceptual difficulties of quantum mechanics, it comes with its own puzzles and controversies. Are these branches real? Do they interact? Can we ever hope to observe them? These questions remain deeply debated, and the many worlds interpretation, like the multiverse more broadly, occupies a space between physics and philosophy. Despite the speculative nature of the multiverse, it has had a profound impact on how physicists think about the universe and our place within it. It forces us to confront the possibility that the cosmos is far larger, far stranger, and far more diverse than we have ever imagined. It challenges the assumption that the laws of physics we observe are the only possible laws, or even the most natural ones. And it raises the tantalizing possibility that beyond the edge of what we can see, beyond the horizon of our observations, lies a vast and infinite reality waiting to be discovered or imagined. At the same time, the multiverse reminds us of the limits of science. There may be questions that lie forever beyond the reach of observation, truths that can never be directly confirmed or refuted. In such cases, we must rely on the elegance and coherence of our theories, on the way they connect disparate phenomena and illuminate hidden patterns. We must balance the desire for empirical evidence with the need for theoretical guidance, recognizing that the two must work together if we are to make progress. The multiverse, whether real or not, serves as a boundary marker, a reminder that the universe may be deeper and richer than any single framework can fully capture. As we continue to explore these profound questions, dark matter, dark energy, black holes, quantum gravity, the matter-antimatter asymmetry, and the multiverse, we are reminded of a simple truth. The universe is still full of mysteries. Despite all our progress, all our theories, all our observations, there is so much we do not yet understand. And that is not a cause for despair, but for wonder. Each mystery is an invitation, a doorway into deeper knowledge, a chance to see the cosmos with fresh eyes. The questions we ask today will guide the discoveries of tomorrow, and the answers we find will raise new questions, more subtle and more profound. This is the nature of science, an endless journey into the unknown, driven by curiosity, imagination, and the quiet hope that somewhere in the equations and observations, the universe is revealing itself, one gentle secret at a time. As we wander deeper into these questions, we begin to see connections that were not obvious at first. Dark matter, dark energy, black holes, quantum gravity, the matter-antimatter asymmetry, the multiverse. All of these mysteries are threads in a larger tapestry. They do not stand alone, but weave together, hinting at a deeper structure beneath the surface of reality. For instance, the study of black holes has led to insights about quantum entanglement and the holographic nature of space-time. The problem of dark energy connects to questions about the vacuum energy of quantum fields and the ultimate fate of the cosmos. The matter-antimatter asymmetry may be linked to the properties of neutrinos and the early moments of cosmic inflation. Each puzzle illuminates the others, and each step forward in one area opens new pathways in another. One of the most beautiful examples of this interconnectedness is the relationship between quantum entanglement and space-time itself. Recent work by physicists has shown that quantum entanglement, the mysterious connection between particles that allows them to influence one another instantaneously across vast distances, may actually be the fundamental building block from which space-time emerges. In studies inspired by the holographic principle and the AD-S-CFT correspondence, researchers have demonstrated that the geometry of space-time in certain theoretical models can be reconstructed from patterns of quantum entanglement on a lower dimensional boundary. In other words, space-time is not a fundamental backdrop, but rather an emergent phenomenon, woven together by the entanglement of quantum fields. This insight has profound implications. It suggests that the fabric of reality, the stage upon which all events unfold, may itself be a manifestation of quantum information. Space and time, distance and duration, may all arise from something deeper and more abstract, something that exists beyond our ordinary experience and intuition. This idea also sheds new light on the black hole information paradox. If space-time emerges from entanglement, then the interior and exterior of a black hole may be connected not just by geometry, but by quantum correlations. The information that falls into a black hole might not be lost, but rather encoded in the entanglement structure between the black hole and the radiation it emits. This would preserve the principles of quantum mechanics while still respecting the insights of general relativity. It is a tantalizing possibility, one that has inspired a great deal of research in recent years and continues to guide the search for a complete theory of quantum gravity. Another profound tool for understanding the universe's history and structure is the cosmic microwave background, or CMB. This faint glow of radiation fills the entire sky and represents the oldest light we can observe, a relic from a time when the universe was just a small fraction of its current age. In its earliest moments, the cosmos was an extraordinarily hot and dense soup of particles and photons, far too dense for light to travel freely. But as the universe expanded and cooled, it eventually reached a point where electrons and protons combined to form neutral atoms, and the universe became transparent. Light could now travel unimpeded, and what we see today as the cosmic microwave background is this ancient light stretched and cooled by the expansion of space itself. The CMB is remarkably uniform, with a temperature of about 2.7 Kelvin almost everywhere in the sky. But when measured with exquisite precision by satellites such as COBE, WMAP, and Planck, tiny temperature variations appear, fluctuations at the level of 1 part in many thousands. These subtle ripples are not random noise, but rather the imprint of density variations in the early universe, the seeds from which galaxies and cosmic structures would eventually grow. The pattern of these fluctuations encodes a wealth of information about the contents and geometry of the cosmos. By analyzing the angular scale and amplitude of the fluctuations, cosmologists can determine the curvature of space, the density of ordinary matter, and the amount of dark matter and dark energy. The CMB has become one of the most powerful tools in cosmology, providing a snapshot of the universe in its infancy and allowing us to test theories of cosmic evolution with remarkable precision. The CMB also carries information in its polarization, the orientation of the electromagnetic waves that compose the light. Polarization patterns arise from the scattering of light off electrons in the early universe and can reveal subtle details about the primordial plasma and the processes that shaped it. One particularly exciting possibility is the detection of a special type of polarization known as B-mode polarization, which could be produced by gravitational waves generated during cosmic inflation. If detected, these B-modes would provide direct evidence for the inflationary epoch and open a window into the physics of the very earliest moments of the universe, a time when energies were so high that they are impossible to replicate in any laboratory on Earth. The search for these signals continues, with new experiments pushing the boundaries of sensitivity and exploring ever more subtle features of the ancient light. As we peer into the distant future, we are also confronted with questions about the ultimate fate of the universe. Based on our current understanding, the cosmos will continue to expand, driven by the influence of dark energy. Galaxies will drift farther and farther apart, and the space between them will grow emptier and colder. Stars will exhaust their fuel one by one and fade into darkness. Over unimaginably long timescales, even the most stable structures will decay. Galaxies will dissolve, black holes will evaporate through Hawking radiation, and the universe will approach a state of maximum entropy, a gentle and final stillness. This scenario, known as the heat death or Big Freeze, is the most widely accepted prediction based on current observations. but the future is not entirely certain. It depends critically on the nature of dark energy and whether it remains constant or evolves over time. If dark energy strengthens, the expansion could accelerate so dramatically that even atoms are torn apart in a cosmic event known as the Big Rip. If dark energy decays or reverses, the expansion could slow, halt, and eventually reverse, leading the universe to collapse back on itself in a big crunch. And there are even more exotic possibilities. Some theories suggest that the vacuum state of the universe might not be stable, and that a quantum transition to a lower energy state could propagate through space at the speed of light, fundamentally altering the properties of matter and space-time in a process sometimes called vacuum decay. Each of these scenarios is speculative, but they remind us that the long-term fate of the cosmos is intimately tied to the deepest mysteries of physics, mysteries we are only beginning to unravel. In recent years, advances in quantum science and cosmology have begun to converge in exciting ways. Quantum sensors, devices that exploit the principles of quantum mechanics to achieve unprecedented sensitivity, are being developed for use in gravitational wave detectors. These sensors could allow astronomers to detect smaller and more distant objects, such as primordial black holes formed in the earliest moments after the Big Bang. Such discoveries could help account for missing mass in the universe and shed light on the nature of dark matter and dark energy. The interface between quantum information science and cosmology is becoming increasingly important, and many researchers believe that breakthroughs in one field will drive progress in the other. At the same time, cosmologists are confronting tensions in the standard model of cosmology. Recent measurements of the rate of cosmic expansion, known as the Hubble constant, have produced conflicting results depending on the method used. Observations of the cosmic microwave background suggest one value, while measurements of distant supernova and other cosmic distance indicators suggest a different, higher value. This discrepancy, sometimes called the Hubble tension, has persisted despite increasingly precise measurements, and it hints that something may be missing from our current understanding. Whether this tension will be resolved by better data, by systematic errors in measurements, or by new physics remains to be seen. But it serves as a reminder that even our most successful theories may be incomplete, and that the universe still has surprises in store. As we reflect on all these mysteries, dark matter, dark energy, black holes, quantum gravity, the matter-antimatter asymmetry, the multiverse, the cosmic microwave background, and the fate of the cosmos, we are struck by a profound realization. Science is not a collection of final answers, but an ongoing conversation with the universe. Each discovery raises new questions. Each answer opens new doors. The more we learn, the more we realize how much remains unknown. And this is not a limitation, but a gift. It means that the journey of exploration is endless, that there will always be new horizons to reach for, new mysteries to contemplate, new wonders to uncover. The universe is vast and ancient, stretching across distances and timescales that dwarf our existence. Yet we, as small and fleeting as we are, have the capacity to ask questions about it, to build theories, to make predictions, to test them against observation. We can trace the history of the cosmos from its fiery birth to the present moment. We can peer into the hearts of black holes and glimpse the structure of space-time itself. We can wonder about other universes, other possibilities, other realms of existence beyond our own. This capacity for wonder, for inquiry, for understanding is perhaps the most remarkable thing of all. And so, as we drift gently towards sleep, let us carry with us the quiet knowledge that the universe is still full of secrets. Dark matter flows invisibly through the galaxies, holding them together in a gentle embrace. Dark energy stretches the fabric of space, carrying the cosmos toward an uncertain future. Black holes guard the mysteries of space-time, challenging our deepest theories and hinting at new physics yet to be discovered. Quantum gravity waits patiently to be understood, promising to unite the large and the small, the cosmic and the quantum. The asymmetry between matter and antimatter reminds us that our very existence is a puzzle, a delicate imbalance that allowed stars, planets, and life to emerge from the primordial fire. And the multiverse, whether real or imagined, invites us to consider the possibility that our universe is just one among countless others, each with its own story, its own laws, its own mysteries. These are the gentle riddles that rest at the edges of human understanding. They are the questions that guide scientists, inspire poets, and fill our nights with wonder. They remind us that the cosmos is not a solved puzzle, but a living mystery, ever unfolding, ever deepening, ever inviting us to look closer, to think deeper, to imagine further. And in that endless journey of discovery, we find not just knowledge, but meaning, not just answers, but connection, a sense of our place in the grand tapestry of existence. As you close your eyes and let your thoughts drift, let them wander among the stars, among the galaxies, among the invisible forces that shape the universe. Let them float through the dark matter halos, ride the gentle waves of space-time, and rest softly on the event horizons of distant black holes. Let them explore the quantum foam, the multiverse, the ancient light of the cosmic microwave background, and know that you are part of this vast, mysterious, beautiful cosmos. You are made of stardust, forged in the hearts of ancient suns, shaped by the same forces that guide galaxies and bend space-time. The universe is singing a quiet song, a melody woven from the fabric of space and time, from the dance of particles and fields, from the expansion of the cosmos and the collapse of stars. It is a song without words, a symphony of mathematics and light, of gravity and quantum mechanics, of dark and luminous, of known and unknown. And tonight, as you drift into sleep, you are listening to that song, feeling its rhythm, sensing its beauty, becoming part of its endless harmony. So rest now, dear traveler. Let the mysteries of the universe cradle you gently. Let the dark matter hold you like an invisible embrace. Let the expansion of space carry you softly into dreams. Let the black holes remind you that even in the deepest darkness, there is beauty and wonder. Let the quantum fields hum quietly around you, weaving the fabric of reality with threads of light and information. And let the knowledge that the cosmos is vast and full of secrets fill you not with fear, but with peace, with the quiet comfort that there is always more to discover, always more to wonder about, always more to dream. The universe is patient. It has been here for eons beyond counting, and it will be here long after we are gone. But in this moment, right now, it is here with you, surrounding you, flowing through you, inviting you to rest, to dream, to drift gently into the night. And as you do, know that the same questions that keep scientists awake at night are the same ones that lull us to sleep. the gentle mysteries that remind us we are part of something far greater than ourselves, something infinite, eternal, and deeply, deeply beautiful. Good night, traveler. May your dreams be filled with starlight and wonder. May the cosmos hold you gently as you drift through the night. And may you wake tomorrow with the same sense of awe and curiosity that brought you here tonight, ready to explore once more the endless, mysterious, magnificent universe that is our home. Sleep well.